All right, good morning. Okay, I was like, hey,
Oh, yeah, sorry.
I was like, yes, hi, awesome. I don't think people whose initials are actually chemical substances. All right, good morning, everybody on Zoom. It's a busy day on Zoom. Ryan, Elsa, Sarah. All right. Alexis present. Good to have you. Jeremy's supposed to be watching this later. Let's start off with an extra credit opportunity for the third exam. A few days late. I'll get sure on this. This is a Valentine's card that my wife got me a couple years ago. And I was super impressed by it, as most things my wife does. But there's a mistake on it. There's one glaring error, and there are two minor-ish errors. But I'm looking for the really big one. There's something on here that within the context of Unit 3, talking about weak acids and bases, is a particularly serious error. Not serious anymore, so it's just calculation of this relationship as indicated on the card. You can get the question wrong every time. So feel free to take a picture, take a screenshot. It's down in my office, which I'll look at there. Oh, that reminds me, Alexis, I apologize. I've taken pictures of those posters, chemistry topic posters. I need to email those out to July folks so you can see what posters look like. I'll get that to you here shortly. Also, I'm just stalling for time in case somebody wants to take a screenshot or take a picture. There is a relationship on here that has a substantial error. And for extra credit, let's do the third exam by a quick description of fix for that relationship. All right, kind of take us in an unexpected direction. These are fire ants. I'm interested in showing you fire ants. Well, fire ants belong to family of organisms called Formicidae, formic, and the word formic is used to name a weak acid called formic acid. That formic acid is going to be the first one I'll tackle as we talk about acids today, and that's our focus. We'll talk about weak acids today. We'll talk about weak bases when I see you on Wednesday. Next week we'll talk about buffers and solubility systems. So when a fire ant stings, the reason why it hurts is because it's injecting a weakly weakly acidic material. Even though it's weakly acidic, it doesn't take large concentration hydrogen ions to really stimulate nerve cells. Nerve cells are very sensitive to ion concentrations. So when we talk about a weak acid, we're talking about a substance that has a hydrogen as part of some sort of carboxylic acid, sorry, as some sort of covalent bond. So the hydrogen is attached, but that pair of electrons is highly polarized. Now, by itself, that polarization does not result in enough enough of the electron density being removed for the hydrogen to fall off. But in this particular bond arrangement, the electrons, if we hold them all the way over to the oxygen, there's room for them because this oxygen can squeeze electrons over. The result is alternate Lewis structure. The result is the hydrogen doesn't have full access to the electrons it needs to hold on to that particular approach. The extent to which a substance is a weak acid depends on how available the electrons are. The more available the electrons are, the more tightly held the hydrogen is, and the weaker the acid gets. In considering whether a substance is a weaker acid or a stronger acid, there are three key criteria. The first is the size. So if we consider the acid we call hydrochloric acid, this is the acid we call hydrofluoric acid. The hydrochloric acid is the stronger acid. Hydrofluoric acid is the weaker acid. Why? Because the chloride is larger. The chloride ion is small. The electrons for the from the fluoride are more available to the hydrogen than the chloride's electrons. The second would be electronegativity. So if we consider HF versus H2O, even though HF was a weaker acid than hydrochloric acid is a stronger acid than water. The fluorine and the oxygen are almost identical in size. So the size is the issue here. The difference is how strongly the respective atoms pull on the shared electrons. Fluorine is more electronegative, electronegative. Oxygen is a little bit less electronegative. And we can keep this trend going if you compare NH3. NH3 is an even weaker acid. It doesn't give up that hydrogen because hydrogen is even less electronegative than the oxygen fluorine. And we can keep that trend going, and CH4 is even less acidic. Why? Because the carbon is now sharing electrons more actively with the hydrogen. So the hydrogen doesn't need to fall off and go by electron goes. Okay, weaker to weakest because they have the lowest electronegativity. The third criterion, the one that I started off with, the example of formic acid, which we're going to come back to as the first real example for calculation, is the idea of resonance. So if I have formic acid, and I have methanol. They both have an OH group attached to the carbon. But formic acid is the stronger acid. The methanol is the weaker acid. Why? Because the electrons can be delocalized, spread out. Why can they be spread out? Because of this double bond oxygen. So if the hydrogen lets go of the electrons have a place to go. There's a three-atom system across which they can be spread. If this hydrogen lets go of the electrons, there's nowhere for them to go. They're just sticking out like a sore thumb. So the hydrogen doesn't really have an ability to let go because the electrons are kind of stuck there. The electrons here are localized. In the event an acid has the capability for multiple resonance structures, multiple Lewis structures, once the electrons are freed up, that generally makes that substance more acidic than if the electrons were stuck in one location. They're localized. For all of these systems, that acidic substance is, for our purposes, going to drop its hydrogens off with water. The result is a protonated water molecule called a hydronium ion, and the rest of the acid we call the economy. This should look familiar. This is exactly what we went over with you last Wednesday, but I'm happy to go over again. So there are two things that we're going to regularly refer to keep track of how good these substances are as weak acids. The first is the equilibrium expression. And specifically what we call the Ka. Sorry, I just saw it. What is the word underneath stronger? And that's delocalized. Thank you, Brennan. Delocalized. Yeah, clean that up. I appreciate you helping. I really appreciate you helping each other out. There's something we can't read. Localized. And just a quick aside, this phrase delocalized is something that shows up a lot in organic chemistry. Lots of situations where carbon has an involvement with electrons. The electrons are not stuck between two atoms. The electrons can move among several atoms. And that gives a range of properties that are fairly unique and also useful in a particular context. So our Ka expression, products. Reactions. So one of the two values is this Ka value. And so essentially what we're saying is as the Ka gets bigger, you're talking about a stronger acid. As the Ka gets smaller, a weaker acid. Now, a variation on this, because the Ka value can change over orders of magnitude, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, 10 to the negative 5, to avoid the use of scientific notation, chemists and scientists will also often refer to the logarithmic version of this called pK. pK is the negative log of the Ka value. Now, the problem is that negative sign. That negative sign flips it all around. So as the pKa gets to be a more negative number, you're talking about a stronger acid. As the pKa gets to be a more positive number, you're talking about a weaker acid. That takes a little getting used to, but it is an important one. Again, especially in organic chemistry, we use pKa values all the time as a quick little label to say how acidic a particular hydrogen is. And it ultimately comes down to a matter of convenience. It's easier to write down a pKa of 5 than it is to say the Ka is 1 times 10 to the negative 5. And that's really what it comes down to. And it's its ability to code switch, to switch from one description to another. As you do it more and more often, it becomes, it's no big deal. I go back and forth through pKa and Ka really fast. It takes a little time to get used to. So just to give you a quick set of values. So the pKa for HF is about 4. The pKa for water is about 15. The pKa for ammonia is about 25. The pKa for methane is about 50. The benefit here is that I can write down the numbers 4, 15, 25, and 50 really easy. I don't have to use scientific notation, I don't have to go exponent, tiny number. The downside is that the scale essentially goes backwards. That 15 is a bigger number, but it is telling me that the negative exponent, that the exponent on the Ka is more negative. This thing is producing less and less hydrogen. 25 more so, and CH4 is more negative exponent. So Alexis, I just saw your question. So would basis be reversed then? I'm going to ask us to call a timeout on basis. I just want to focus on acids today. But you are definitely heading in the right direction. So what we're going to see is that there is an inverse relationship between if something's really good as an acid, its conjugate or leftover acid molecule part is really bad at being a base. Because the properties are inverse. Acids give up hydrogen as bases pick them up. So it gives up hydrogen, the rest of the molecule doesn't want to pick that hydrogen back up. It has to do with its size, electronegativity, resistance. Something that's a really big ion doesn't hold on to that hydrogen ion very well. It's a smaller ion that's going to hold on to that hydrogen ion a little better. So if you do get that fluoride ion by itself, it will pick up the hydrogen to some extent. Now, the other catch with pK value is that each step is a power of 10. So the difference between 25 and 50 is not 25, it's 10 to the 25th, which is a huge difference. It's a very different substance in terms of their acidic. So what pK offers in convenience, it takes away in terms of amount of information you have to unpack. Questions about the pK? You're not supposed to be experts at pK values right now. I'm just letting you know they're out there. They're coming for us. We're going to get ready. I got to clear a little bit of space. Any questions before I clear the board here? So the other value that chemists will regularly use is the pH. So acid HA in water, making hydronium ions, leaving the conjugate behind. that conjugate on occasion will pick up a hydrogen again. Turn that hydronium back into a water molecule. So we can either keep track of the Ka value, or its logarithmic equivalent to pKa. Or what we could do is keep track of the hydronium ion concentration, because hydronium ion concentration is effectively the active indicator of where this equilibrium is participating. But again, there's a logarithmic equivalent called the pH. So pH is defined as the negative logarithm of the hydronium concentration. Again, that results in this backwards situation. Graphical reminder. If you have a low pH, close to 0, on a 14-point scale, you actually have the most hydronium ion. As you get closer and closer to a pH of 14, you have less and less hydronium. The other thing that's going on in solution is something called the hydroxide. The reason why these two are tied together is because water molecules are always reacting with each other and establishing their own background equilibrium. That water molecules collide into each other and on occasion will transfer a hydrogen. That water acts as its own acid and its own base to itself. You don't have to have anything else there. But what it does is provide a conveyor belt, a mechanism to adjust what the hydrogen and the hydroxide concentrations are in a given solution. And they're always going to be tied together. Now we can write equilibrium expression for this. If you write a full-blown one, we could say Kc for everything. H2O plus, hydroxide, water times water. Now these water concentrations are large and effectively constant, so we're going to treat them as part of the constant. And so we get a new relationship, which is an important one for us. W for water, specifically for water. Hydronium, hydroxide equals 1 times 10 to the negative 14. Now this value of 1 times 10 to the negative 14 is actually established from what we call conductivity measurements. How well does electricity flow through pure water? And it turns out it doesn't flow very well. If you have absolutely pure water does not conduct electricity well. Now, I should point out that, that does not mean put the toaster in the bathtub to try this out, because that's not absolutely pure water. And your skin has got lots of salts on it, and your body has lots of salts in it, and you'll conduct electricity just fine. Absolutely pure water does not conduct electricity very well, but it does conduct electricity a little bit, and that little bit can only be explained by water reacting with itself. But for better or worse, there's a logarithmic version of this. If you take the negative log of everything, we get pKW equals pH plus POH, which equals 14. This relationship is going to be incredibly useful for us because as we begin to talk about weak gases, we're going to keep track of that hydrogen ion and then report on the hydrogen ion logarithmically and say, hey, here's pH. When we get to talk about weak bases, we'll keep track of the hydroxide ion. And we'll want to report a POH, but chemists have agreed to keep track of the hydrogen ion. That's an arbitrary choice. That means we can go from acids and bases. We're just using the same scale, keeping track of the hydrogen ion on a scale, logarithmic scale of 0 to 14. In the middle, pH 7 does not mean that there is no acid or base. It means you have equal amounts of hydronium and hydroxide. So pH plus pOH equals 14. That's a key relationship. Okay, so we're going to keep track of the Ka, or its logarithm of pKa. We can keep track of the hydrogen concentration, or its logarithm of pH. And the weak bases, we'll keep track of hydroxide, or its logarithm of pOH. And then use this most recent relationship to report back out the pH value. So finally, that formic acid. Now, as we begin to deal with weak acids, you know, we can always write out the chemical structure, but it's also perfectly okay to write HA. It's a shorthand notation. I want to focus on the chemical structure in this particular example. Get us our opportunity to talk about that. There are two hydrogens in this molecule. One of the hydrogens is part of a non-polar carbon-hydrogen bond. That is not the hydrogen that's coming on. Not all hydrogens in the molecule are safe. You have to have the hydrogen part of a polar bond. So you got to have that electroactivity difference. And to enhance the acidity, it really helps to have this possibility for resonance. That the electrons, if they're available, can be distributed across a multi-atom system, like a possibility. In the presence of water, we provide more detail in terms of the electrons. We're saying the electrons from water are more available. These electrons have a place to go. So in the forward direction, we're getting that hydronium ion, and then what we would call the formate ion. I'm just drawing the alternate resonance form here. Get all the little dots. You don't have to have the dots in. I'm just trying to be as possible. Now, just a quick note about charge. If you notice on the left-hand side, these are both neutral molecules. On the right-hand side, I've got one thing that's positively charged and one thing that's negatively charged. And that's okay because the net charge is still neutral. You can't have a chemical equation which starts out with no charge and ends up with some net charge. That means something got dropped or something got added to need to account for. It's okay to shuffle the electrons. It's okay to shuffle the hydrogen around. And the result of moving this positive hydrogen over to the water molecule is the formic acid remainder got more negative because it now has an electron all on its own, and the water got more positive because it just had to share a charge with an extra positive hydrogen. So if you see charge appear, it should add up to be whatever the charge was at the beginning. Now that conjugate base has electrons, and those electrons can pick the hydrogen back off the water, and then that water molecule can pull electrons back from the hydrogen. Oops, sorry. Take that a little better out. The big one. It's great for the hydrogens. That results in the water being regenerated and the formic acid being regenerated. Formic acid. Formate ion. So the substance that we call formic acid was first identified by taking a whole bunch of fire ants and grinding them up, trying to extract the particular substance which causes stinging irritation. Now, I've never been stung by fire ant. I'm sure you've been stung by one.
It hurts.
Yeah.
Yeah.
My experience is not with ants. My experience is with nettles. It's a type of plant that has little fine hairs on it. And if you grab onto the plant, the hairs stick you, and they have formic acid as well. And they hurt, but they don't go after you. The plant stays put. If you step away from it, you don't have to worry about it coming after you. So that's kind of nice. But do you mind if I ask you, where was the incident?
Arizona
Arizona.
or Texas, one or the other, probably both.
Is it something where you had some sense it was in the vicinity, or you just were like walking? And all of a
Probably
sudden-
wasn't paying attention. Yeah.
And it's with the for me with passage of time, it's actually it's a fond memory for me because it's in my grandmother's backyard, and it's something I can't blow my mind. just silly American not realizing that in England you can get plants that sting you. But in all seriousness, it is possible to die from ants. If you are unexpectedly encountering these fire ant nests, it's possible to get enough stings, enough formic acid to be potentially dangerous. So, I'm very glad you will get. So we can we can set up a rice table. If we know the initial concentration of the formic acid is 0.1 molar, we're not going to keep track of the water. We're saying initially there's none of the hydronium or formate ion present. As we come to equilibrium, we're going to use up a little bit of the formic acid, take a bit of hydronium, take a bit of the formate ion. Write our Ka expression. H3O plus. Products of reactants. And then we have to go to a table. So there's a table that's available to you from the textbook. So list alphabetically, here's acetic acid. Ascorbic benzoic. There you go, there's formic. Now notice how they've rendered this HCOOH. That COOH is the shorthand for this group of atoms we call in organic chemistry, we call it a carboxylic acid. It's understood in this style that the first oxygen is doubly bonded and the second is the OH. That arrangement is common enough that chemists have their own shorthand for it. So that formic acid reacts with water, makes a chromium ion, the formate ion, and we have a Ka value here of 1.77 times 10^4. Ka variance up here. Immediately next to it is the pKa value. We're not going to use that immediately, but we'll come back to that in a couple of days. 7.7 to -4. So I've got X, minus X. 7 times 10^4. I guess we can always use decimals. So let's switch over to decimals here. So 0.004. 1. Those are 4. One 1195. I'm gonna write out the ridiculous number sentence. Let's see if this before we start rounding. 0.04. All right, so what I want to do is pause for a second. I pointed this out to you guys on Wednesday, but I want to do it again. Whenever we have a subtraction term and the Ka is fairly small, there's a reasonable expectation that the subtraction term is inconsequential. So I'm going to do this in an alternate approach. I'm going to assume that x is pretty much 0. That's a really small number. Now, I already know from decimals that it is a pretty small number, 0.004195. What I want to do is just solve it on my calculator here. 1.77 second exponent -4 times 0.1. And I'm going to take the square root of that number. So by approximation, I get x equals 0.004207. If I do it exactly using decimals, so that minus x term is included, you might say explicitly we're solving everything, not making any approximations. I get 0.00411195. Now those answers are not the same, but if I just go to the first decimal, or sorry, first 2 digits, I got 42 versus 41, and the proximity gets even better as the Ka gets smaller. So if this becomes 10^5, the difference between these two becomes inconsequential. We're right on the edge here. 10^4 and a concentration of 0.1. That's close enough where you can almost see the difference in the next decimal place. Next significant decimal place. So long story short, on the exam, you're welcome to continue using decimals, or you can make approximations if you so choose. Using the exact answer, I'm going to figure out what the pH is. pH is the negative log of the hydrogen concentration, which we have indicated with x. It's negative log of 0.00411195. I get 2.385. Questions? Now, as we get to acids that have bigger Kas, meaning that they're stronger acids, I would expect you to just use decimals because that subtraction term is going to start to get more and more, have more bigger impact on the bottom of the fraction. But if you've got a factor of 1,000 difference between the K value and the concentration, is perfectly okay to make the approximation. What I want you to do is just make sure you can see the result here. Because what we're going to do is try a different weak acid. For acetic acid. Now, acetic acid's chemical structure looks like this. The difference between acetic acid and formic acid is that there's a carbon here instead of a hydrogen attached to the C double bond OH. Its bonding arrangement is what chemists refer to as a carboxylic acid. Now, it's arguably the most important of the weak acid patterns because it shows up in biological systems all the time. Carboxylic acids serve two important roles biologically. It's kind of an overall summary for you. The first thing carboxylic acids do is they act as a really important handle for molecules. That carboxylic acid group, it's the way that our biology grabs onto carbon chains. So that carboxylic acid acts like a sticky patch, a little place to grab on with other atoms. The other thing, in the other direction, carboxylic acid is the last step before carbon dioxide. And under the right conditions, that carboxylic acid will turn into carbon dioxide and then it's exhaled. Both a handle and the last stage of extracting that last little bit of energy before the carbon dioxide returns to its, we say, fully oxidized state. Now, it's not necessary to write out the whole chemical structure of a molecule to keep track of what's going on for the weak acid in that molecule. So we can write down HA in place of the entire structure. It's only this hydrogen we're keeping track of. That's the H. That hydrogen is the one that we're keeping track of. A is the rest of the molecule, the whole thing. Hundreds of atoms. We just represent with the A. It's just the rest of the molecule. Let's say its initial concentration is 0.1 molar. Use up a little bit, make a little bit, make a little bit. 0.1 minus X. Ka. Products, reactants. The difference is the Ka value. If we're talking about acetic acid, we'll go back to the table. Here's acetic acid at the top. Acetic acid. Now, just a quick note. There's a column we haven't talked about here. This step. There are some acids that have more than one acidic hydrogen. And so, for example, arsenic acid has one hydrogen that comes off, then a second hydrogen comes off, a third hydrogen comes off. For our purposes in unit 3, we're only ever going to talk about one hydrogen at a time. We're going to talk about this monoprotic, one proton systems. Acetic acid has one acidic hydrogen. Now, I should also point out, those 3 hydrogens do not come off easily. That does not mean you cannot remove them. You need to have a really, really good basis to do it. And so these are not easily removable hydrogens. Easily removable hydrogen has a Ka of 1.76 times 10 to the negative 5th. 1.76 times 10.
Will you always have 0 concentrations for the?
No. So that's where we're going to go next week. We'll talk about buffers. So in a buffer, there will be a substantial concentration by conjugate, and that's going to nudge the equilibrium back towards the reactive side, which is going to have an impact on the pH. We're always going to assume concentration 0 for the hydrogen ion or hydroxide. Now, just a quick summary. Formic acid. You don't have to recopy this. You've already got it all in your notes. Just kind of emphasize this distinction. Ka was 1.77 times 74. Pka 6.75. Acetic acid. .76. Here's the key, times 10 to the negative 5. 10 to the negative 5 is 1/10, 10 times smaller than 10 to the negative 4. So this Ka value is saying there are going to be less products, that you're going to have less ionization, that you're going to get less hydrogen ion. And the pKa is a more positive number, 4.75. It's a stronger acid. It's a weaker acid. I can tell formic acid is the stronger one because the Ka is a bigger number. pKa is a smaller number. I can tell the acetic acid is the weaker acid because its Ka is smaller, is indicated by the scientific notation. Its pKa is bigger number. We have chemists everywhere. I apologize for the backward style of the logarithmic notation. pH and pKa both the same thing. So the deeper question is why? We're about to solve the rice table. That's the easy part. The deeper question is what's going on between formic acid and acetic acid? It has to do with this group right here. And here's the stepping off point, because most of y'all take organic chemistry, hopefully me, but at some point take organic chemistry. These bonds over here are impacted by these bonds over here. That the electrons between atoms don't stay put. Their influence, I should say, doesn't stay put. And the electrons between any two atoms can impact the electrons between other atoms. Why? Because one end of the bond is the same carbon that's also attached to these bonds. That these electrons over here interact with these electrons over here. And so the more carbons I put here, you can check this out. The look for the molecule that has one carbon attaches, you get two carbons, it's called propanoid, three carbons attached. As you have more carbons attached, this Ka just keeps getting smaller and the pK keeps getting bigger. Now it begins to level out once you have about 5 carbons stretching out here. You don't get any weaker as far as the acid. So that tells you there's a limit to the interaction over a certain distance. But that when we begin to talk about carbon chains, the electrons from one carbon atom can interact with and have an impact on neighboring. All right, so on to the Desmos. We got our expression. Nice part is it looks awfully similar to what we just did a few minutes ago. All I have to do is change to the -5th. But that means I have to go find my parabola here.
Gotta fix your,
Oh, thank you. Got -5. That's good. While we're zooming in here, I should point out not all insect stings are based on formic acid. So if you get stung by a critter and it hurts, it's not necessarily formic acid. Formic acid is just one of the ways nature's come up with to make our lives miserable. Bees and hornets, for example, they're injecting an enzyme. That enzyme causes inflammation processes. A whole bunch of aquatic organisms. I mean, separate from insects. Now, if you remember back previously, our answer was 0.004 from formic acid. You can already see we're at a lower number, 0.001. So we get less hydrogen ion out of this, which we would have expected as K is smaller. All right, 0.00132. What I want to do is one more time, I want to just assume that this is pretty close to 0. Just want to see what we get now. Let's your acid. 1.76 second exponent -5 times 0.1. Square root of that answer. If I make the approximation, I get 0.00133. We're pretty close. Better as we move to weaker acids. So again, the approximation is a reasonable approach. You guys have decimals. That's most the approximated value. Question. Okay, so using the table. What's the pH? Oh, I'm sorry, I forgot to calculate the pH. pH is the negative log of that concentration. 0.00132. Uh, 2.88. You guys remind me what pH calculated in formic acid?
2.385.
2.35. Yeah. So the pHs come up, which indicates it's less acidic. Why? Because it's not doing the hydrogen ion respectively. Why? Because that carbon next door is providing extra electron density to help hold on to the hydrogen. neighboring set of 1 carbon and 3 hydrogens is enough to make a difference. All right, what's the pH? 0.25 molar benzoic acid. Random pro tip, you don't actually need the tables in the back of your book. This is something that's listed on Wikipedia for all of these substances. It's that important. It's an important characteristic of describing the substances. Find PA, find the Ka value or PK value for any substances. In the case of benzoic acid, benzoic acid 6.25 times 10 to the 5th. Over X. And I should point out, as I have decimals up, this motif, this recurring pattern of x squared over concentration minus x equals whatever the K value is. This is going to hold true for our weak acids and our weak bases. And then for our buffers, the only thing that changes for our buffers, we're going to have to add a concentration term on the top of the fraction. It's possible to have multiple equations running in decimals, so you can acceptable for you to kind of create template equations, which is kind of ready to go. I spend more time finding things than finding travel and anything else. Zero, 039. So pH would be the negative log of that. At 2.41 would indicate this solution is more acidic than our previous gas solution. The lower the pH, the or available hydrocarbon. Now, the other thing to keep in mind is, as we're doing these calculations, we're not considering any strong acids. If there were a strong acid present, there'd be no reason to bother with these calculations. This would be a rounding. This 0.00392 would be a rounding error for hydrochloric acid. Hydrochloric acid ionizes completely. So if you have hydrochloric acid, you've got 0.1 molar in hydrogen plus 0.00392 is a little bit more acidic. Yeah, not more. So my assumption is that there aren't any strong acids in play. There's a crazy plant commonly found in South Africa. And the name itself, for us, we don't speak Afrikaans, which is Dutch. Dutch analog. Giftblar. And the plant makes this fluoroacetic acid. So there's a fluorine attached to that first carbon. Fluorine is an electronegative atom. And so fluoroacetic acid so it's, you remember the pKa for acetic acid. pKa for acetic acid was 4.75. You put one fluorine on instead of a CH3 group, you have carbon with a fluorine attached. We're now at 2.586. So we're down almost a full unit on the pH scale. Remember the pKa scale. pKa scale is a logarithmic scale. So this stuff is 10 times more acidic than acetic acid. But that fluorine also introduces some interesting chemistry. It binds to certain things in the way organisms process carbon molecules. In particular, let's see. So if cattle eat this stuff, cardiac arrest is soon to follow. And then if you come in contact with it, not just contact with the plant, it's enough to induce severe by sensitivity. It's a really reactive molecule. And it's always crazy to me. I don't understand. I'm just fascinated by the fact that the plant has incorporated fluorine, all things. It's not something that normally gets incorporated in biological molecules. But because of that fluorine, this molecule is now 10 times more acidic than it would be without that fluorine. Let's call it there. When we get back together on Wednesday, we're on a weekly basis. It's picking up hydrogen to some extent. You guys have to fully wrap up. Check the chat box. Yep, that's it. That's it. Just thank you guys. Thanks, Elsa.
Okay.